when you look in the far field, again, it looks like expansion of cold atoms, but this is the far field of these lasers, you get this bright spot, which is actually the Fourier transform of each individual small laser. So you have sum of intensities and you have some of these spots. If somehow all these lasers have the same phase, in this case all have 0 phase, then the far field would look like that, and you would have this sharp Bragg diffraction peak that would tell you that now you have phase coherence between the lasers, and this is our experiment. I want to emphasize that the coupling between the laser needs to be dissipative. So this is part of an emerging understanding. In many fields, the dissipation is sometimes your friend, and it helps. In this case, there's a loss in the system. That's the dissipation, which depends on the phase of the lasers. And the coupled lasers, by mode competition, which is an exponentially strong process, would dissipate into this minima loss state. So what you want to do is to make sure that the minimal loss state of the system is what you want. In this particular case, the minimal loss state, by this dissipative coupling, is when all the lasers have the same phase, and that, as you can imagine, is useful if you want, for example, to cut something and to take all the energy of all the 1,500 lasers into this single spot. If you look on this area, as compared to this area, the ratio between them measures quantitatively how many lasers are phase lock. Are all of them phase lock or just a fraction? So in this particular case, the ratio between these two areas is about 1,500, which indicates that indeed, in this case, all the lasers are phase locked. Let me also mention that in order to couple the lasers, you have to send light from one laser to the other, and this is very easy. Light can easily go anywhere. So there are many, many ways of coupling the lasers, starting with nearest neighbor coupling, which is what you see here, to mean field, namely the light from each laser goes to all the other lasers. It's a bit more hard to do with other oscillators, and many other, I'll only give the 2 examples, so nearest neighbor and mean field. So this was the coupled laser part, and these are the students working on the project with me in the Weizmann Institute. Let me tell you a bit what is a hard problem. And let me also say that I may have been invited here to speak about cold atoms. I'm not sure, so just to be safe, I'm going to show a poster tomorrow on cold atoms and not on lasers. So this is roughly my definition of what is an easy problem of optimization. So you have to find the minimal value as a function of parameters, and you see this is easy. If I start here, there are many ways to find the minima, and a hard problem is usually characterized by this complex landscape. So if you change the parameter, the value can get many local minima, and this is the correct minimization solution, for example, of a traveling agent problem. And the problem is not to get stuck in one of these local minima, and also the fact that really hard problems, and for example, computer scientists characterize these problems like NP-hard, BNP, etc. So they are speculated to have the global minima only marginally different than one of the local minima, and this might even be exponential scaling with the size of the problem, say the number of cities the traveling agent has to go through. So you can already see why it's really hard to find the best solution rather than this one of these local minima or many local minima. So as you know, we know all, for example, in the cold atom business, we know how to map many hard problems into other problems where we can actually synthesize a Hamiltonian. So in this case, this is going to be the energy, and our goal is to find the ground state of the Hamiltonian. And to do that, we have to cool the system from the outside, and I added here simulated cooling or simulated annealing. Sometimes people say quantum annealing, because you have to be very clever and resourceful to overcome these local minima and somehow not to get stuck in them and to find the global minima. This is not easy. Let me suggest a different approach, and this would be our laser system. So this is not a parameter, it's the laser phase. Remember, we have 1,500 lasers, so actually we have 1,500 errors or dimension in a complicated Hilbert space. Let me also emphasize we are looking to find the ground state of a classical Hamiltonian. So the solution is classical, but this is still a hard problem, and it's also interesting in the sense that you can map it to other useful hard problems that people care about. And now I'm going to follow a sort of suggestion made by Yoshi Yamamoto some time ago, and he said, let's not come from the top, let's come from below. So we choose a gain of the laser system to be below any of these solutions. So here there's no lasing mode, and there is spontaneous emission, which you can roughly think about all the possible solutions coexist somehow. There are a lot of arguments, what is exactly this state? Is it a thermal state? Is there entanglement? Is there squeezing? This is under controversy, but the general idea is now go slowly, and again, how slowly you have to do it is another open question, but suppose you do it, you don't want to reach this guy. If you do it slow enough, you just touch this correct solution, you come from below, so you don't see these solutions at all, and then this crosses the threshold, started to laze, and by mode competition, sucks up all the energy and becomes a classically macroscopic solution. So that's the general idea. And you can see this list of people, Bayer, Feyer, Mabuchi, and Yamamoto. This was a Stanford group. They built what they call the Ising machine. Now Yamamoto is in Japan, so he gets lots of money from the Japanese government, and he also gets a lot of news coverage. So it says Japan builds first quantum computer, but then a few months after that, so the Japanese cabinet decided this is not a quantum computer. So as I told you, there is controversy even at the cabinet level, because it's their money. But I want to take a step back and just to give you a flavor what you can do using this phase locking, how you can engineer the system so the phase locking state will solve some problem. So let me tell you what I mean when I talk about phase locking. So I look on two lasers and I interfere them on the screen, and I don't see interference fringe there because the phase fluctuate, but if I couple them with this dissipative coupling, then the phase difference, the phases still fluctuate, is constant, and I get these stable interference fringes. This is what I want to see. And in our system, now we want to have 1,500 lasers, not 2 lasers. So we cheat a little bit, and we take actually a single laser. In this case, it's a YAG laser. Here are the 2 mirrors, and here's a mask with 1,500 holes. So the first thing we have to ensure that these lasers, which are quite close, about 100 microns, do not couple by themselves. And to do that, we build this telescope inside the cavity, F. So it's 4F, it's images and inverts, and then another 4F, so 8F. So light coming from each one of these holes comes back to the hole, does not couple, and that's how you see this far field. You see, our experiment is made of light. We don't have to diffract light from it. It diffracts itself and tells us what is the solution. It's sort of convenient. If you want to couple them, for example, with nearest neighbor, we have to spoil this imaging condition. For example, apply a little bit of defocusing, move this mirror a little bit. We actually move it to half the Talbot distance of this grating, and we get this anti-phase locking. This is 0 pi solution, and again, you see these sharp, bright points, and to explain you why this is negative, you can either think about the half Talbot as giving pi phase between neighboring as you go back and forth, or you can just think that if you go back and forth and you have the negative phase between, pi phase between neighbors, you have destructive interference in between, and this minimizes loss. So this gives you some intuition. If I move the mirror just a little bit more, this is the full Talbot distance, I get what I showed you before. Okay, so it works on a, say, semi-large scale, more than 1,000. So we can talk about statistical physics and things like that, not 2 or 4. Actually, we would be tempted to simplify the system, and I'll do it for a few slides, and then I'll tell you that it's not always correct. And the most simplified way to think about a laser is a classical oscillator which has a single degree of freedom with its phase. Forget about intensity, forget about polarization. And if you assume that, so the phase is a number between 0 and 2 pi, classical number, and you can map it into a spin and call it an XY spin, and then this 0 pi configuration would be nothing but an antiferromagnetic solution for the XY spin. So it's a nice analogy. But let me state that there is a mathematical identity, which is written here. So the quantitative model that describes this approximation, approximating a laser dynamic as phase oscillator, is called Kuramoto. It's well known. For example, it describes people clapping their hands in a synchronized way, which I hope you will. And to find the steady state of this Kuramoto model actually can be shown mathematically to correspond to the ground state of the XY model with the same coupling matrix. Okay? Not the excitation spectrum, not the dynamic, just the ground state. Ground state is mapped to the steady state. Does it work? So I showed you one example. These are a few other examples. We can put our lasers or the mask on a hexagonal lattice, say graphene, or on a triangular lattice, and look on the diffraction pattern. Whenever we see sharp peaks, we know there's long-range order in the system. So there's a unique ground state, and we compare it to, we open a book on the XY model, and we get the correct solution. Okay? Sometimes we fail, And this is an interesting failure. You know, in physicists fails, you can make sort of an interesting claim out of that. So this is called the Kagome lattice. It's similar to the triangular, but now each triangle, which contains two possible solutions in the XY, namely a vortex and anti-vortex, is not coupled to the next solution if we're only talking about nearest neighbor interaction. So it turns out that this Kagome has actually an exponential degenerate ground state. This is called geometric frustration, and the number of degenerate ground states is 2 to the power of the number of triangles, 2 to the power of 500. Okay, finite entropy at 0 temperature, and our poor laser system cannot find a unique ground state, just because there are exponentially many. So it found this thing. It's not completely orderless, but you don't see sharp Bragg peaks. And it's interesting to show that it actually exactly matches some calculations that were made many years ago on magnetic materials which show this property. But this was never measured in real magnets. Also, what we can do with our lasers, that is hard to do with real spins, we can change the coupling very easily. For example, move the mirror a little bit more and generate a little bit of a next nearest neighbor interaction. For example, interaction between this. And this breaks the degeneracy, and then we get, again, sharp Bragg peaks. Okay, so it's very flexible. We can put them on quasi-lattices, on disorder lattices, but I'm going to skip that. So it's a ground play, and we can actually simulate the XY model. Yeah, there's 10. In many ways, but let me go back to the question of easy versus hard. So until now, I showed you relatively easy problem, which have this unique ground state, or I showed you the impossible problem that has exponentially many ground states. But what about one of these harder problems? So for that, just to simplify, what happens when the system has many stable ground state, we just take an array of lasers on the ring, and we use topology, if you want, the boundary conditions which are periodic, and this means that under this Kuramoto dynamic, all these discrete vortices, e to the im phi, it's a discrete vortex, are locally stable. They cannot be unwided locally. They are topologically protected. So this one would be, for example, one of these topological protection. And then the Kuramoto will start to dissipate and might get stuck in one of these, and we can actually map the phase of each laser. We can interfere it with a local oscillator, so we can map the exact state of the system. And then we find the following. So we have a parameter, I'll tell you in a moment why, and we look on the pump strength. So it's the pump divided by the threshold pump. So 1 is threshold. If you remember in my introduction, the threshold was a special point where good decisions can be made by the system. So the price of an error of not choosing the exact ground state becomes intolerable, and mode competition becomes strong. So you would expect to have good performance of the system as you get closer and closer to the threshold, and indeed you see that both by the experiment and by the full laser rate equation, including intensity fluctuations, we actually get this strength. Whereas the Kuramoto model, which is the mapping to the XY, which I showed you before, completely fails. It doesn't care about intensity. So what's going on here? I'm going to skip the microscopic explanation and just tell you one fact about this system. It turns out that to find a global solution, usually you have to go slowly. But what is the time scale in our system? I didn't provide external cooling, so I cannot control it. So it turns out that this parameter actually controls the time scale by which the system can find a solution. And as you go closer and closer to threshold, it takes slower to stabilize on a solution. And this is good. And to quantify this, we have this Kibble-Zurek mechanism, which is a general framework, which tells you that you need to find 2 time scales that govern the dynamic of the system toward the ground state, and then you look on the success rate, or in the language, the coherence of the system, and you try to collapse it on a ratio of these 2 time scales. So we have partial success on that. We have these 2 time scales. One comes from the phase, one comes from the amplitude. There's this annoying 0.6, which I cannot explain. So this is not real quantitative Kibble-Zurek, it's just qualitative. But what you can see, that the success rates of the system for many different parameters depend on the ratio of 2 time scale. At least it shows the point that the dynamics towards minimizing the system is very important, and you have to do it slow. And this gave us this news and view, which I don't like so much, and it says that our laser model is relevant to cosmology. Maybe it is. I think I'll skip the part of disorder, and I'll skip the part where I show mean field versus nearest neighbor interaction. I don't have time. So I want to go to a different set of problems. I want to remind you, these spin problems are cruel. There is a computer scientist sitting somewhere and ranking your problem. how hard it is. It's NP hard, it's not NP hard. So this is annoying. And hard problems in their definition are really hard. Let's go to a plan B. And the plan B would be, let's solve problems that everybody really needs, and they are reasonably hard, okay, in day-to-day life, and they are in optics. So we want our photons that find a solution to have a useful solution. And I'll give you 2 examples of that. The first example is how to focus light through scattering media, or in our case, through a tissue. So we took a tissue of chicken, and if you send a perfect plane wave and you have a perfect lens, this is what you get. It's not the laser to blame, it's not the lens to blame, it's the scattering by the tissue. And what I want to show you, and there are ways to correct it by putting here spatial light modulators and playing with the phases, but this takes a long time. What I want to do is to take all these things and to put it inside our laser system, and I want to make sure that the good solution, focusing to a point, will minimize the loss in the system. How do I do it? I put an aperture here in the far field, the pinhole, and I close it until it's a delta function. So now, when this diffuser goes in here, the phases here of the different points will be chosen such by this mode competition that after going through the tissue, they will focus to a perfect point. Okay? And we get about 100-fold increase in the peak power here as compared to here. There's a lot of background here. It's only partial success that you don't see. That by image processing, we make it disappear. And this happens very fast. So what we did, we took this chicken breast, we put it on a motor, we rotated it as fast as we could, so we got a different realization of disorder every few hundred nanoseconds. And this is only an upper limit. We tried to rotate it fast, and everything broke. So the laser has to solve a new problem every few hundred nanoseconds, and it can do it, actually, the theory says, and also our preliminary measurement, it takes only a few round trips to find these solutions. Or one of the, this is, by the way, I'm not saying this is the globally most stable solution, as we said before. I have one slide. So this is one example. Let me give you another example. So here's again our laser. Oh, okay, sorry. So now here's the laser, and now we put the diffuser here, but we put an entire image. Here's the image. The way we impose the laser to laze as an image, this is called a degenerate cavity, and it's known in the literature to support all the possible modes. So it's every light distribution, for example, the digit 5, is a mode of this cavity. Remember, it's just image upon itself by the 8F telescope, and that's the definition of the mode. It's self-consistent. But now we have a problem. Now we have a diffuser inside, and this is harder, and if I put the diffuser out of the cavity, this is what it does. It scrambles the digit. But you should already not be surprised that if I do things inside the cavity, then the phases of this mode, which are not determined yet, will be such that they will do some trick. I will not tell you this trick now. Before in the aperture, you knew what the trick was, to focus to a point. Here the trick is to find the flat points on the diffuser and to go there. And when you do that, you compensate to some extent the effect of the diffuser. And this is an entire image, and this is how to do, to image an entire image through a diffuser. My last example would be a very famous problem in optics. I'm sure many of you know it. What happens if I take an object, I scatter light or X-ray, I measure only the intensity, and I want to reconstruct the object. So the phase is missing. So it's called the phase problem. And what I'm showing you here, this is the intensity of the diffraction pattern of some object. The phase is missing. So what do? We want our laser to find the missing object, and we have to do 2 things. The first thing, we have to impose this intensity of the diffraction pattern as the boundary condition, and as we do with the spatial light modulator. This is the $25,000 Hamamatsu. You have to be really careful when you insert it into your laser cavity. So this is one, and now the phases will be determined by the laser, and we need to find the exact solution, the correct solution, so we want to impose some loss. And the loss we are going to impose is again put an aperture, and the aperture will follow the external contours of the original object. So we don't know what the object is, but somebody told us what is the size. Mathematically, it's called compact support, and it's a common assumption in this inverse phase problem. Okay? So now, the phases, the correct phases, will give the correct object that will be within the compact support that will minimize loss. And this is the object that we see, and this is the missing object. And this is not an easy problem. So I won't define whether it NP hard or not NP hard, and again, this happens very fast. So I gave you just a few examples, and the chairman is standing. So I just showed you that the ability to phase lock many lasers, say more than 1,000, although I remind you that we cheat a little bit, because we only took one sort of big lasers and divide it to 1,000, we can simulate XY spins, sometimes with the Kuramoto, or if you want the XY in the imaginary time, it's sometimes called, and sometimes we want to go beyond Kuramoto to enhance the probability to find the global ground state. And I skipped this one, and I showed you that it can be solved to practical problem, like how to scatter through tissue or chicken breast. This experiment, by the way, was nominated to Ig Nobel, but we didn't get it. So at least we have our claim to fame. I was told Humboldtian, 55 Humboldtian got Nobel Prize. One of them, me, almost got Ig Nobel because they called it the Schnitzel laser. So they found that it's funny to put a chicken breast inside your laser. But somebody did something more funny, so we didn't get it. And I showed you how we can reconstruct objects by knowing only the intensity of the Fourier plane and asking the laser itself to find the correct phases by minimizing the loss of the system using this compact support assumption. So thank you very much.
Thank you, Nir.